Hello, everyone. Mr. Chaffa again. Part two of the video demonstrating some homework questions from homework 5.5, 5.6 about double and half angle identities. Again, this is not a replacement for the normal instructional videos. It is simply something to hold you over until I finish those. But for some of you, this might be sufficient to understand and get through the assignment. When I'm finished creating the actual content videos, of course, I will let you know. In the previous video, we had worked a few questions, the last of which was to write the expression as a sum or difference of trig functions. We were given 2 sine of 57 degrees times cosine of 91 degrees, and we had done that by using, I'm sorry, you can't see the question. Let's try that again. This is the question that we had done at the end of the previous video. Write the expression as a sum or difference of trigonometric functions. 2 sine of 57 degrees, cosine of 91 degrees. We had accomplished that by using the correct product to sum identity. And since the problem, the expression that we were trying to rewrite was a sine times a cosine, then we went to the correct formula, which was sine times cosine. Now, the expression we had a 2 in front of it, which really didn't change anything because the 2 just sat there while we applied the sine cosine product formula to 57 degrees and 91 degrees and ended up getting 1/2 times sine of the sum plus sine of the difference, but the 1/2 and the 2 canceled. We did end up with a sine of negative 34 degrees, and I do remember, and you may remember, especially if you just wrote the video, watched the video, that when we entered sine of 148 degrees plus sine of negative 34 degrees. It didn't like it. It wanted us to apply the even odd identity to sine and basically pull the negative out. In this video, I'd like to demonstrate a few more examples of problems in this homework. Let's start with number 7. This is just a product to sum, so we would do the same thing. The only thing we would have to do is make sure we pick the correct formula. Since this is a cosine times a sine, we would want to pick the formula that has cosine times sine, which would actually be this one down here. So we would apply it in a similar fashion. Let's take a look at number 8. Same thing. We have a product of two sines, but notice this time the arguments have x's in them, which is perfectly okay. If we wanted to convert a product of two sines, we would just have to go to this formula, which again would pick up the 1/2, but because there is an 8 in front of this product, that 8 would get multiplied by the 1/2 to make 4. And now we're going backwards. Use the sum to product identity to rewrite the expression. We will work this one out since it's our first sum to product identity. Even if it didn't say use a sum to product identity to rewrite the expression, notice it's a sum of two trig functions, sine of 7 alpha plus sine of 4 alpha. Because it's the sum of two trig functions, we want to find something that is the sum of two trig functions, which in this case was the sum of two sines. Our question was the sine of 7 alpha plus sine of 4 alpha. So we're going to apply this formula to that problem. All right. I think for the benefit of, no, I was going to type it, but I'll just draw it. Okay, so we're looking at sine of 7 alpha plus sine, I believe it was 4 alpha. Let me double check real quick. Yes. And we want to use the correct sum to product identity. The identity that we want is the one that says sine of A plus sine of B. It is equal to 2 times sine of half the sum times cosine of half the difference. So let's write that as our formula. Come on. Sine of A plus sine of B is equal to 2, I believe it was sine, wasn't it? Yes, sine of half the sum, also known as the average, times cosine. I'm going to do myself a favor here. I'm going to zoom in, erase this, and write it a little bit better. Plus, it'll give me a little bit more space. All right, so again, we are applying the formula sine, come on, draw, sine of A plus sine of B equals 2 times sine of half the sum times cosine of half the difference, A minus B. So all we have to do is set up the formula, but replace the A with 7 alpha and the B with 4 alpha. So we would have 2 sine of 7 alpha plus 4 alpha over 2 times cosine of 7 alpha minus 4 alpha over 2. And then just simplify this as much as we can. Because the sum is an odd coefficient, 11 alpha over 2, and for the difference, 3 alpha over 2. I think this is probably the point where they would expect us to stop, since the fraction can't be reduced any further. Let's see. 2 sine of 11 alpha over 2. Now, to get the alpha, I did type backslash alpha. If you hover over this, it'll tell you that's how to type it. And then it was cosine of half the difference, so 3 alpha over 2. Parentheses in the wrong place. And I believe that's how they want the answer. Yes, it is. All right, so be careful when the problem shifts gears. The previous question gave you a product and wanted a sum or difference. This one gave you a sum, or it could have been a difference and they wanted a product. So I imagine this will carry over for a couple of, okay, so there was only one. Now, when we get to this next batch, these are problems we've seen before. When we did the sum and difference problems, where we're told a trig value function and a quadrant, and we're asked to find something else. Let's see how long this goes on. 10. Here's some trig functions, find some more. Let's see. Here's some more. Okay. And there's some more. So the good news is we don't have to demonstrate a lot of these. Well, there's 3 of them in a row, so let's take a look at number 10. Actually, I want to take a look at number 11. Use identities to find the value of sine and cosine of the function for the given angle measure. So I don't like the way this is worded. The previous question is a little bit clearer. Find sine of 2 theta, et cetera, et cetera. Here it's, well, okay, it says find cosine of 2x. Okay, so we're given tangent is equal to 2, cosine is greater than 0. We're going to be asked to find cosine of 2x and sine of 2x. Tangent is equal to 2, cosine is greater than 0. Let's take a look at it. Given tangent of x is equal to 2 and cosine of x is greater than 0. I believe it said greater than 0. I'll check real quick. Yes. And we're being asked to find cosine of 2x and sine of 2x. All right, so this is going to be pretty straightforward. There's a lot of moving pieces in here, but let's start with what our goal is, which is to find cosine of 2x or sine of 2x. Let's find sine of 2x first. Now, to find sine of 2x, we need the right formula. The right formula is a double angle formula. Sine of 2a equals 2 sine a cosine a. And if we apply that here, we would get, I'll type this as long as I can. For sine of 2x, that's equal to 2 sine x cosine x. I guess I can put these in parentheses to be consistent. You don't always have to put parentheses around the argument of a trig function. If the argument is a little bit chunkier, it's a good idea, but it's never wrong to use it. So if we want to find sine of 2x, then we need to know the value of sine of x and cosine of x. We currently know neither. What do we know about x? We know its tangent is 2, and we know its cosine is greater than 0. That's actually very helpful because we could use identities to transform tangent into some other trig function, or we could just draw a good picture. First, we got to figure out the quadrant. You know which quadrant we're going to be in when tangent is 2 and cosine is greater than 0. Well, let's start with where tangent is positive. Tangent is positive in 3 and 1. Of those two, where is cosine positive? Well, not in quadrant 3. So we're actually in quadrant 1, which is pretty good. Now, x is representing the angle here, so you really have to be flexible with what variables represents. I know x normally is the x coordinate, but here, because it's the input of the tangent function, it represents that angle. And speaking of the tangent function, this is where you have to be ridiculously careful, because the definition of tangent in terms of x's and y's is y over x. But the x down here is not the same as the x up there. That x up there is the angle. Now, if using one letter in multiple capacities in a single problem throws you for a loop, change one of the letters. The only ones I wouldn't change are x and y when they're referring to the x and y axis. I could just as easily have worked this problem if I changed the x to, say, a w everywhere I have it. It's not going to change a single thing that we do. But what it does do is it relieves the x of double duty. In this case, x was representing both an angle and, of course, the x coordinate when we set up the definition of tangent is y over x. But to remove that confusion, we can just change the name of the variable inside the trig function to something else. The work will still be the same. So let's call the angle w. I guess I could have called it theta or something like that, but typing a theta in here is not the easiest thing to do. As I draw a theta, how about a w? W. There we go. All right. So back to this task at hand, which is to figure out what sine of w and cosine of w is. What are we told about tangent? Well, we're told tangent is equal to 2. But what is the definition of tangent? Tangent is y over x. So if we can deconstruct the 2 as a ratio, we can call its numerator y and its denominator x. We can make anything a ratio by putting it over 1, and therefore assign a value of 2 to the y and 1 to the x. A real quick Pythagorean theorem would give us the square root of 5 for the hypotenuse. And now we've got this triangle ready to give us all the trig functions that we want. So in that triangle, what is sine of w? What is sine? Opposite over hypotenuse. Why am I typing? I'm going to have to draw a square root sign. Sine is opposite over hypotenuse, so 2 over the square root of 5. What is cosine? Well, cosine is adjacent over hypotenuse. Or I could use x, y's, and r's. Sine is y over r. Cosine is x over r. X is 1. R is the square root of 5. So since sine of w is equal to that and cosine of w is equal to that, then sine of 2w is equal to 2 sine of w cosine of w, which is equal to, time to draw because we have square roots, 2 times 2 over the square root of 5 times 1 over the square root of 5. And if we put the 2 in front over a 1 to treat it like a fraction, then we just multiply across the top to get 2 times 1 is 4, and multiply across the bottom to get 1 times the square root of 5 times the square root of 5 is 5. There's the value of sine of 2w. And what's the value of cosine of 2w? Well, the thing about the cosine double angle formula is that you have choices. The cosine double angle formula is equal to any of these three. We can choose the one we want. We currently know the value of both sine and cosine, so any of them would do. In fact, let's just use the top one. Cosine is equal to cosine squared w, cosine of 2w is equal to cosine squared w minus sine squared w. Cosine of w was 1 over the square root of 5. That gets squared. Minus sine of w was 2 over the square root of 5. That gets squared. That leaves me 1 over 5 minus 4 over 5, which is equal to negative 3 over 5. So it's just using an identity plus the given information to find the values of the trig functions necessary to implement that identity. I have a quick follow-up question. If sine of 2w, well, what happened there? If sine of 2w is equal to 4/5, but cosine of 2w is equal to negative 3/5, what quadrant is 2w in? Well, where is cosine positive? Excuse me, where is sine positive, but cosine negative? And the answer is there. So without even doing any extra work, we know that 2 times W would be in quadrant 2. W was in quadrant 1. 2 times W was in quadrant 2. So W had to be more than 45, but less than 90. All right, let's go back to the homework for a second. Put in these answers. Cosine was, now the second one we got, it was negative 3/5. And sine was positive 4/5. And by the way, if I wanted tangent of 2W, I could just put the value of sine over the value of cosine. Work smarter, not harder. 12, I believe, was the same idea. Given that cosine of 2 theta, wait a second. This one's interesting. I didn't pay close attention to this one. Use identities to find the value of sine and cosine for the following angle measure. Find theta given that cosine of 2 theta, or find sine of theta, given that cosine of 2 theta is equal to 28/53 and theta terminates in quadrant 2. Well, the fact that theta is in quadrant 2 tells us sine is positive, but how can we go backwards? Can we go from cosine 2 theta to just sine? And the answer is very carefully, yet very straightforward. To go from cosine of 2 theta to sine, look at this identity. If we know cosine of 2 theta, we would put it on the left side and we would set it to equal to 1 minus 2 sine squared theta. Then we could just solve for sine by subtracting 1 from both sides, dividing both sides by -2, then taking the square root. Stay cognizant of the quadrant of A to know whether the square root comes out positive or negative. So this one kind of flew under the radar. I thought it was just like the previous one. But on the previous one, we were given a trig function of x and wanted to know trig functions of 2x. Here, we're given a trig function of 2 theta and want to know the function of theta. So just think and choose the correct formula and use it to get what you want. 13 is a different type of question. Decide whether the positive or negative square root should be selected. This is an introduction to the half angle formulas. If you looked at the half angle formula chart, excuse me, looked at the half angle identities on your formula chart, you see they're all cosine, sine, or tangent of half an angle, and 3 of them are equal to plus or minus a square, excuse me, plus or minus a square root. So looking at one like this, we're not being asked to evaluate anything, but decide whether or not the square root should be positive or negative. The sign of the square root depends upon the original angle and the quadrant. Well, in what quadrant is 263.5 degrees? Well, going through quadrant 1 is 0 through 90. Another quadrant takes us to 280, and then down to quadrant 3 would take us to 270, but 263.5 is less than 270. This would be in quadrant 3. And in quadrant 3, sine is negative. So this is a pretty easy question to answer because really on the left side, it's just quadrant and trig function to determine positive or negative, a game we've played before. 14 is the same thing. All right, use a half angle identity to find the exact value. Let's see what we have down here. Find a value, given this, find that, and I bet the rest of them are given this, find that. Actually, this one and this one are different. All right, so I see 3 more questions I want to go over. One where we actually find a value. We'll go back to number 15. And then one where we have one trig function value, we found another. And then these last two, which ask us to capitalize on an identity to write the expression more simply. So let's go back to 16, or was it 15? Yeah, I want to do 15. Use a tangent of half angle identity. Wait, wasn't that something different a minute ago? Hmm. Use a half angle identity to find the exact value of the following expression, tangent of 22.5 degrees. Well, let's look at our half angle identities. For tangent, we have 3 of them. They're all correct. Which one do you think would be easier to use? I say not the first one because it has a square root and we have to make the plus minus decision. But notice the other two don't have square roots and actually don't ask us to make the plus minus decision. How convenient. I will probably go with one of those. What question were we being asked? Excuse me. Find tangent of 22.5 degrees. Okay. Tangent of 22.5 degrees. And it explicitly said to use a half angle formula, but I knew to use a half angle formula because if you double 22.5, that's 45 degrees. We're going to use the middle one, sine of A over 1 plus cosine of A. All right. Tangent of 22.5 degrees. If we're going to use a half angle, we need to think of this as something divided by 2. Well, what would you cut in half to get 22.5? Well, double 22.5 and it'll tell you the answer is 45. So we're going to set up the tangent half angle formula with 45 degrees. And I'm going to use the middle one. Tangent of A over 2 is sine of A over 1 plus cosine of A. So tangent of 45 over 2 is sine of 45 over 1 plus cosine of 45. Let me double check to make sure I didn't get them backwards or mix up the sign. Sine over 1 plus cosine. Yes. And we know the values of both sine of 45 degrees and cosine of 45 degrees. Whether it's by a right triangle or a unit circle, they're both equal to the square root of 2 over 2. So we have square root of 2 over 2 over 1 plus square root of 2 over 2. Now, we're going to have to clean this up a lot. And if you took a look at the answer choices, because this one was multiple choice, how are these answer choices different than what we currently have? Well, what's similar is that they all have a square root of 2. But what's different is there's not a fraction in sight. So if we're going to get one of these four answer choices, we need to do the necessary moves to get rid of all these fractions. First thing I would do is multiply both sides of the big fraction by 2 because it matches the denominator of the little fraction. So when we distribute and multiply, when we multiply across the top and distribute across the bottom, all the little fractions should disappear. On the top, the 2's cancel, leaving square root of 2. On the bottom, when we distribute, 2 times 1 is 2 plus, and when we, on the right side of the addition, the 2's would cancel, leaving a square root of 2. All right, that's not bad. It's obviously better than it used to be, but is it the best answer? Well, not if our goal is to get one of these, which still have no fractions. So how do we make that happen? Well, when you want to get rid of an addition or subtraction problem in the bottom of a fraction that has a square root in it, you multiply by the conjugate. So we're going to multiply both sides by the conjugate of the denominator, which is formed by simply changing the plus in the middle to minus. We're going to multiply both sides by 2 minus the square root of 2. Now, what happens as a consequence? Well, on the top, when we distribute, let's go yellow, the square root of 2 gets multiplied by the 2, which doesn't do anything. They just get put next to each other. But when I multiply it on the other side, something will happen. So on the top, we would get 2 times the square root of 2 minus the square root of 2 times itself, or the square root of 2 squared. But wait a minute, square roots and squares cancel each other. So it would just leave me with 2. And on the bottom, if we FOIL it, the first product would be 2 times 2 is 4. The outer is 2 times negative square root of 2, which is negative 2 square root of 2. The inner is positive 2 times square root of 2, excuse me. And the last is positive root 2 times negative root 2. Positive times negative is negative. Square root of 2 times square root of 2 is square root of 4. And now we clean this mess up. Nothing happens on the top. We get 2 square root of 2 minus 2. But on the bottom, okay, I see a 3 that should be a 2. It's been a long day. On the bottom, these terms cancel. And then we have 4 minus the square root of 4, but the square root of 4 is 2. So the bottom is really 4 minus 2, which is just 2. And now that the denominator is a single term, we can clean this up. There's a couple of ways to do it. One way is to split this into 2 fractions by putting them both over a 2 and then reducing or canceling. On the first fraction, the 2's would cancel, leaving a square root of 2. Well, the second fraction is 2 divided by 2, which is 1. So it looks like it's square root of 2 minus 1. I believe that was an answer choice. None of those say square root of 2 minus 1, except one of them does. Do you see which one it is? Now, here they rearrange the order of the subtraction problem. So whenever you have a subtraction problem and you want to look at it through a different lens, keep positive things positive and negative things negative. In this answer, the square root of 2 is positive, but the 1 is negative. So if I were to rearrange I don't know why it does that. If I were to rearrange the order of the pieces down there and put the 1 first, then it would be a negative 1 followed by a positive square root of 2. And negative 1 followed by positive square root of 2 is answer choice C. All right, two more quick questions. Let's do one of these givens. Let me look at the two. Let's do this one because we already did a cosine half angle. Given that cosine of alpha is 4/5 and alpha is between 0 and pi over 2, so alpha is in quadrant 1, determine the exact value of cosine alpha over 2. All right, cosine's 4/5, alpha's in quadrant 1. Got it. Cosine's 4/5. I'm memorizing the problem. Cosine is 4/5. Cosine of alpha is 4/5, and alpha was in quadrant 1. And we're being asked to find cosine of alpha over 2. Pretty sure that was it. Let me double check. Yes. All right. Well, if we're going to do this, first thing we need to do is, well, there's a few things we could do first, but I'd like to know which quadrant this angle is in because the formula for cosine has a plus minus. The formula for cosine of alpha over 2, or more generically, the half angle formula for cosine, does have a plus minus in front of it. And the sign that we choose depends upon the quadrant that a over 2 is in. Or in this case, alpha over 2. Where we're told where alpha is, and that's not supposed to be an equal, it's supposed to be a less than. We're told where alpha is, but we want to know where alpha over 2 is. So we can take this compound inequality, divide everything by 2, and transform it to 0 is less than alpha over 2 is less than pi over 4, which is still in quadrant 1. Pi over 4 is 45 degrees. If you're between 0 and 45 degrees, you're in quadrant 1. So what that means is when we take the square root, we're going to use the positive version. That's not a good place to put it. We're going to use the positive version because we're in quadrant 1. All right, the formula for cosine of alpha over 2 would be plus or minus, we already negotiated that, the square root of 1 plus cosine alpha over 2, or cosine A. So this is 1 plus cosine alpha over 2. But what was it we were asked to find? Oh, cosine of alpha over 2. Notice that we now have the cosine alpha in our expression, and we were told that cosine alpha was 4/5. So I simply have to substitute 4/5 in there and try to clean this up the best that I can. All right, equals the square root of 1 plus 4/5 over 2. Now that square root is over everything. At this point, we could either add the 1 plus the 4/5 on the top, or we could try to get rid of the fraction inside the big fraction. I choose the latter. I'm going to multiply both sides of this by 5. My life, your life, everybody's life is better if fractions don't have more fractions inside of them. Multiplying both sides by 5, we get a 10 on the bottom. And across the top, when we would distribute the 5, we would get 1 times 5 is 5, and 4/5 times 5 is 4. That's equal to the square root of 9/10. But we can distribute a square root across a fraction. So square root of 9 over the square root of 10. Square root of 9 is 3. And I bet it's not going to like it if we leave the square root in the denominator. So if we multiply both sides by the square root of 10, we get 3 square root of 10 over 10, which should be the final answer, but we will check. 3 square root of 10 over 10. 3 square root of 10 over 10. 3 is not where it belongs. I'm going to see if it takes it. Interesting. 3n square root of 10 tenths is not what that says. This actually says 3 times the square root of 10 over 10. I would not advocate writing this answer like this. I would advocate, I was just seeing if I could break the website. Apparently I didn't. I would definitely write it like this because when you see something like 3 and 4/5, you're not thinking 3 times 4 over 5. You're not thinking multiplication. You're thinking addition. You're thinking 3 and 4/5. So writing that answer like I typed it in just as a goof, the 3 in front makes it almost look like a mixed number with an irrational fractional part. But so I would not do that. I would put the 3 on top where it belongs to clearly state that this is a multiplication problem. All right, we're going to take a look at number 19 real quick, and that'll be the last video. Use an identity to write the expression as a single trig function. This is the type of problem where you're given the right side of the identity and you're asked to turn it into the left. There's that one, and there's this one. We'll take a look at this one. Simplify the expression plus or minus square root of 1 minus cosine of 18 theta over 1 plus cosine of 18 theta. Come on. All right. So we want to simplify plus or minus the square root of 1 minus cosine of 18 theta over 1 plus cosine of 18 theta. My brain wants to say 180, but that is 18 theta, not 180. All right, we need an identity that is going to help us do this, help us simplify it. So we're looking for an identity that has a plus minus square root, which means it's a half angle identity, but it has 1 minus cosine on top, 1 plus cosine on bottom. Do you see it? It's kind of messy here. Let's clean this up. The one we are looking for is right here. So the right side of this is the formula for tangent of a over 2. This is the formula for tangent of a over 2. But wait a second, we don't have an a in here. We have a 18 theta. So out with the a, in with the 18 theta, and then 18 divided by 2 is 9. So that expression is equal to tangent of 9 theta. Let's go put that answer in and then wrap this up. Tangent of 9 theta. Check it. Do a victory lap. And I think I've shown you all of the quirks, twists, turns, idiosyncrasies of this homework assignment. I am still working on the content, namely proving or deriving these identities. I will not be doing separate instructional videos right now about how to work these individual examples since we have this and the previous long video that does that for us. All right. Hope you learned something.